Okay, guys, welcome. Today we're going to talk about functions. Now, I'm sure that you've already talked a decent amount about functions in your previous math courses, but we're going to consider it sort of in a different lens, but a lot of things that you already know about functions will carry over to what we're going to discuss now. Now, a function is a set of ordered pairs such that any two pairs that have the same first coordinate have to have the same second coordinate. Right? Or another way you can think of it is that a function does not contain any ordered pairs for which the first coordinate is repeated for different second coordinates, right? So you can't have the same first coordinate going to two different y coordinates. And that's just like the way that you've studied functions before. Now, just as a quick example, we have that this set represents a function because you have 1, 2, 3, and 5 as your first coordinates, and none of them repeat, so you're good. And you could even see that your second coordinates repeat, right? You have a 3 here and a 3 here, but that doesn't matter, right? Now, we'll talk about special kind of functions in a little bit. This would not be what's called a one-to-one function, but this is a function nonetheless. Now, the second set given here would not be a function because you have this first coordinate of 1 being repeated for two different second coordinates. All right, so that would not be a function. Okay, now the next thing that we will do is look at the domain of a function. And again, this is probably something that you've already considered before. Now, the domain of a function, which we'll sometimes denote with DOM and then in parentheses the function itself, is the set of elements where we have A such that there exists a B where that ordered pair A comma B is an element of that function, right? And if you've never seen that backwards E before, that just means there exists. So the domain of a function is the set of all elements A such that there exists a B such that A comma B is in your function, right? So it's what you can think of as all possible first coordinates of your function, right? Such that a second coordinate, of course, is defined for it. Now, the range of a function is sort of the opposite, right? It's the set of all B's such that there exists a first coordinate A such that that ordered pair A comma B is an element of your function. Now, if the domain of F is A and the range of F is B, sometimes we'll write that F is a function that goes from A to B by saying F colon and then A and then an arrow pointing to B, right? So F is a function that takes elements from A to B, right? So that's a fairly common way of saying that. Now, another thing that we will usually do notation-wise is that instead of saying that A comma B is an element of a function, we usually say, just like you're usually more accustomed to, that F of A is in B. And of course, it's understood that A belongs to your set A and B belongs to your set B. And of course, this is the domain and this is the range. Okay, now let's look at an example. Now, both F and G here are functions. We have F is all the ordered pairs X comma X squared, such that X is a real number, right? And G is the same thing, except X is an integer, right? And these are both functions, but what do their graphs look like? Well, F is all the ordered pairs X comma X squared, which another way you can think of this is that this is just Y is equal to X squared, right? And of course, we all know what this graph looks like. It looks something like this. Okay. Now, the only reason why this one looks like this is because don't forget that X is always a real number. Now, for G, we have the same thing. We have X squared. So we can think of this again as Y equals X squared, but here X is an integer, right? So we have to be a little bit more careful here. Now, instead of your graph being connected, you only are going to have values at all the integers. So you're going to have a value at 0, then you're going to have values at 1 and -1, and then at x equals 2, y equals 4, and x equals -2, -4, and so on and so forth. So this graph will not be connected, right? So you're going to have the points of the parabola, but just at the integer x values. Okay. Now, part B is the function where we have, or I should say the relation, is the relation where we have x comma square root of x, where x is a real number that's also positive. Is that a function? Well, again, you can think of this as y equals square root of x. And here we'll take of this to be just the positive or the principal square root function. And essentially what we mean by that is that we don't end up with the plus or minus business, right? So of course this will be yes, right? If you didn't take this to be the positive or principal square root and you have plus or minus, then of course you do have the issue where you have repeated values. But the square root function, of course, looks something like this, right? For x being positive or equal to 0, right? And of course, one way you can kind of cheat is to use the vertical line test. That still works here. Right, so that's another thing that we can use. Now, the last one is sort of more of a disclaimer. Is the empty set a function? Well, technically, yes, right? Because the empty set doesn't have any elements. So for all the elements that are in there, you don't have repeats, right? No repeating first coordinates. So technically, yes, it is a function, right? Even though it's sort of a silly one, technically it does satisfy that definition. Okay. Now the next type of function that we'll talk about is what's called one-to-one. And this is one, again, another concept that you've probably already heard of before. Now, a function is one-to-one if for any two pairs of f with the same second coordinate, that would imply that they have the same first coordinate, right? So this is sort of meaning that no y values can repeat or second coordinates can repeat. Right? Now, another way you can think of this, and this is usually how we go about proving it, is that a function is one-to-one if for any x's and y's in your function, right? And I really should say x and y in your domain. So let's say domain of f, right? Then evaluating the function at both of these values, if they are equal, that implies that the inputs would have to have been equal, right? And we'll do a couple of examples of that. Now, a function f is onto, and we say that it's onto the codomain or onto the range, if the range of f is b. So that means that if there's an element in your range, that means that there's some x element in the domain that will get you there, right? So you can find some x value that will get you to any element y in the domain. So let's go ahead and let's do a couple of examples. So we want to determine if f that takes natural numbers to the integers is one-to-one and or onto, right? So to determine if this is one-to-one, we can assume that f of x1 is equal to f of x2. And we want to show that this implies that x1 is equal to x2. Well, let's do it. If we have f of x1 equal to f of x2, then that means that x1 plus 1, because that's what my f is equal to x2 plus 1. Well, then if we subtract 1 from both sides, they both cancel out, and we get that x1 is equal to x2. right? So since that happens, this is 1-to-1. Okay, so that's how we can show that it's 1-to-1. Now, how about onto? Well, to show onto, you essentially assume that you have that y is equal to, let's say, b, right? Is there an x such that f of x is equal to b? Well, if f of x is equal to b, that means that x plus 1 is equal to b. And then, of course, we could solve for x, and we would get that x is equal to b minus 1. So it appears that we've found the formula here, right? But we have to be kind of careful, right? Because we're going from the natural numbers to the integers, right? Now, this b, since it's a y value, has to be an integer, right? So it looks like, for example, what if I wanted to get a negative integer, right? So let me come over here. What about negative integers? Right? So say -3, right, which is an integer. There is no x in the natural numbers such that x plus 1 is -3, right? Because this x would have to be a natural number, right? So since this happens, this means that this is not onto. Right? Now, if it were the other way around, if I wanted to go from z to n, then of course it would be onto, right? Because then I would have my elements. I could attain any element that I want in the natural numbers by picking the appropriate integer. Okay, let's look at another one. So in this next one, we have f going from the natural numbers to the natural numbers, and our function is f of x is equal to x squared. Right, so let's show 1-to-1 first. Well, if we have that f of x1 equals f of x2, then here we'll have x1 squared is equal to x2 squared. Now the problem is that once you take a square root, you're going to have plus or minus x1 equal plus or minus x2. And this is not able to be brought to x1 is equal to x2. Right? So this is not 1-to-1. Okay, now let's take a look at onto. Okay, well, again, so we would assume that there's a y in our b, right? Is there an x that would get us there? Now, again, the key is that we're going from natural numbers to natural numbers, right? Now we're taking natural numbers to their squares. So what about non-perfect squares? Right? What if we had, say, y is equal to 3? Well, if y is equal to 3, then I would need to take a number squared and get 3. So I would need x to be the square root of 3. Well, again, x is the natural numbers, so this is no good. So again, this is not onto. I think close that. Okay, so this is not onto. Keep getting these notifications here. So this is not onto. Right? Because I would need a natural number to go in, and I need that natural number to be square root of 3, which of course can't happen. What if we open it up to the real numbers? Do I get 1-to-1 and onto? Well, the one-to-one will still be the same, and it's not one-to-one because of the same reasoning before. All right, well, what about onto? Right, well, now this argument doesn't work, right, because I could plug in a square root of 3 because now I'm dealing with real numbers, right? But we still have to be careful because if we're squaring a number, what about negative real numbers? Right, so say y is equal to -2. Well, then I would need x squared to be -2, right? Which of course can't happen because then I get x is equal to square root of -2. But my x has to be a real number. So this is again no good. So this is not onto. Okay, so finally, if we look at the case where we have positive real numbers to positive real numbers, then it looks like that fixes all of our issues because now the one-to-one proof would look like x1 squared equals x2 squared. But then when I take square root, even though I do have the plus or minus here, I'm only entering in positive values, right? So I don't have to worry about the negative. So this is now one-to-one, right? Because I can't plug in a negative number. Now for onto, we've eliminated all the issues where we have, for example, square roots of negative numbers, because now we're only plugging in positive numbers and getting out positive numbers. So now I don't have this issue, right? So now the proof looks like this. Assume y is equal to b. Show that there exists an x in the real positive reals such that f of x is b. Well, my f of x is x squared, so x squared is equal to b, and if I take the square root of both sides, I get x equals square root of b, and of course, I'm only interested in the positive case this time, so I'm good here, right? So this is onto, right? Can find this every time. Right, so it's a little bit weird at first, but the idea usually goes to looking at your domain and your codomain and sort of thinking about, are there any odd cases that I should worry about? And if there's not, usually you can solve based on what your f of x is. And as long as your x is allowed to equal, right, whatever that is, as long as your x belonging to your domain can be that, you're usually in good shape. Now, our next definition we have is what's called a bijection. We say that we have a bijection if a function from a to b is both one-to-one and onto, right? So bijection would be for both one-to-one and onto, and sometimes this is called a one-to-one correspondence. Right, but most of the time we'll say bijection. Now, if f is a bijection, so it's both one-to-one and onto, then we can talk about what the inverse of f is, right? So if we have a bijection, then the inverse exists, and we define it to be the set of all ordered pairs that are sort of flip-flop, right? All of our first coordinates are now all of our second coordinates, and all of our second coordinates are now our first coordinates. Right, and of course, sort of I don't know if it's maybe a theorem or more or less a corollary, but if f is a bijection from a to b, then its inverse is also a bijection, but it just goes from b to a. Now, the last sort of interesting thing that we'll talk about in this video is the idea of proving that two sets have equal cardinality. Now, we know that two sets A and B have equal cardinality if there exists a bijection from A to B, right? Now, the set of natural numbers and the set of natural numbers but union with the singleton 0 have the same cardinality, since we can define a bijection by taking x minus 1, and for every natural number that you plug in there, you're going to get a natural number in addition to 0. And you're going to hit every single number, right? So is it 1 to 1? Well, yes, because if you have x1 minus 1 equals x2 minus 1, then you can conclude right away that x1 and x2 are equal. And of course, is it onto? And of course, yes, because assume y is equal to b, right? Does there exist an x in A? In this case, x in A is your natural numbers, such that f of x is equal to b. And of course, yes, because if f of x is equal to b, you have x minus 1 is equal to b, and you would get x is equal to b plus 1. Now, since b is a natural number or 0, right? If you plug in 0, you get 1, which is a natural number, so that's okay. If you plug in the next natural number, 1, you get 1 plus 1, which is 2, which is another natural number. So you can always do this. So since that's true, this is onto. And it's 1 to 1. All right, so we found a bijection from the natural numbers to the set of natural numbers plus 0. And since we've done that, then that means that the cardinality of the natural numbers is the same as the cardinality of the natural numbers plus this one additional element. All right, which may seem weird at first, but since we're able to do this, that's true. So let's do another example. Let's show that the natural numbers and the integers have the same cardinality. So this might be somewhat surprising, but let's show that there exists this bijection. Now, what you can do for something like this is let's go ahead and let's look at the natural numbers. We have 1, 2, 3, 4, 5, 6, so on and so forth. Now for the integers, we could say that we have 0, we could have 1 and -1 and 2 and -2 and 3, -3, and so on. Right? Now, in sort of a lazy way, we've shown this, right? Because we have that we're going to hit all the integers, and no natural number is going to give you the same integer, right? So you have a one-to-one function here, right? So I'll leave it as an exercise. Maybe I'll give this as a homework problem to find the explicit function for this. Right, and my hint is to do this. My hint is to find a piecewise function for the even and odd numbers. You know what? Let's go ahead and actually do this, and then I'll leave the next one as an exercise, since that one's sort of the same idea. Now, sort of the key here. So, following the hint, let's look at our even numbers. It looks like for all of our even numbers, we're just dividing by 2. So let's say that our f of x, again, is piecewise here, and we'll say that it's x over 2 if x is even. Right? And of course, all my x's here are natural numbers. Now, what if x is odd? Right? Then it looks like what I want to do, and of course, let me just list the next one here. The next one would be 7, and I'd want that to go to -3. So it looks like we're getting the odd numbers here, and we also need to sort of do something where we're maybe subtracting 1 here, right? Because I need to go from 1 to 0, from 3 to -1, from 5 to -2, something like that. So it looks like if we do something like x minus 1 divided by 2, and maybe take its negative, will that do it for us? Right? So if I plug in a 1, that would give me 0. If I plug in a 3, that would give me a -2, or sorry, I would get a 3 minus 1, so a 2 over 2. So I get a 1, but take its negative, and that would give me -1. If I plug in a 5, I would get 5 minus 1, which would be 4, right? And if I divide that by 2, that would give me 2, and then -2, so that works. And then if we do 7, it looks like we would get -3, right? So it looks like this would be the bijection that would work, right? And of course, this is something that would take a little bit of practice and a lot of trial and error to get used to, but eventually you could show that this is a bijection, right? Or you find that this is the proper bijection, right? Now, to show that it's one-to-one and onto, of course, you would do the same thing, right? So if x is even, you'd have that x1 over 2 is equal to x2 over 2, which would imply that x1 is equal to x2. And if x is odd, so this is showing one-to-one here, right? If x is odd, then we would have that minus x1 minus 1 over 2 is equal to minus x2 minus 1 over 2. And if you multiply both sides by -2, you would get x1 minus 1 is equal to x2 minus 1. So x1 is equal to x2. Right? So in both cases lead to one-to-one. Right? And then, of course, to show onto, let's assume that y is equal to b. Not element of, that it's equal to b. Now, remember that y here is an integer, right? So for any integer, can I plug a natural number in to get this? So is there an x in the natural numbers such that f of x is equal to b? Well, again, my f of x it's either x over 2 or it's the negative x minus 1 over 2, depending on if it's odd or even, right? And this is equal to b. Well, if my x is even, then I would have either x over 2 is equal to b, so x is equal to 2b, right? And if my x is, if it's odd, then I would have minus x minus 1 over 2 is equal to b. And it looks like that would give me an x minus 1 is equal to a negative 2b, right? If I multiply both sides by -2, and then I would get x is equal to negative 2b plus 1. Right? And it looks like this would work for b being positive, right? That would give me all the positive natural numbers. And if b is negative, I would multiply it by -2 to make it positive and add 1, and then that would give me all the natural numbers, right? So this is onto. All right, so that's how we can show something like that. Now, the next one I'll leave as an exercise, but let's sort of prove lazily for now that the rational numbers has the same cardinality as the natural numbers. All right, now, this is a fairly famous result, sort of known as Cantor's diagonalization argument. All right, so what we're going to do is we're going to list out all of our possible fractions sort of in a systematic way. So let's say we have 0 over 1, 0 over 2, 0 over 3, 0 over 4, and we'll go to 5, let's say. Right? So in this first row, all my numerators are 0, and then all of my denominators are changing. So in the next row, let's make all of them 1. And 1 over 5. And then we have 2 over 1. 2 over 2, 2 over 3, 2 over 4, 2 over 5. Then we have 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5, so on and so forth. All right, and we'll do 4 and 5, and then we'll explain the argument. Okay, and then 5 over 1, 5 over 2, 5 over 3, 5 over 4, 5 over 5. And of course, these also go down this way now. Now, here's what we do, right? So we're going to start at this corner, right? And that, of course, would give us 0. Now, we're going to come around here, and we're going to go on this diagonal. Now, we've already mentioned 0, so I'm going to cross out 0 over 2, since that would just be a repeat. But now I get a new one. I get this 1 here. Then we circle around, and we come back here. Now we have 2 over 1. I have 1/2, which is new. And then I have 0 over 3, which I mentioned again, so I'm going to cross it out. So cross it out, 0 again, and then I have 1/3, which is new. And then I have 2 over 2, which is 1, which I've already mentioned, so I'm going to cross that one out and then keep going. And then we get 3. Right? And then we just keep sort of circling in this pattern. 3 over 2 is new, so we'll include that. 2 over 3 is new. 1 over 4. 0 we mentioned, so we would come back around. The next 0 would get crossed out, and we would choose 1/5. Now 2 over 4 we've mentioned because that's 1/2, so cross that out. 3 over 3 we've mentioned, so cross that out. 4 over 2 is 2, which we mentioned, so cross that out, and then just keep going. Right? Now, eventually, you'll get to every fraction this way, right? Now, one thing that you might be saying is, well, what about all the negatives? Which is true, because the rational numbers do include the negatives. So the way that we would list this out now, so let's have our natural numbers up here. 3, 4, 5, 6, 7, 8, 9, 10, and then I think it'll be clear what the pattern is. So the first one, of course, will make our 0, right? That's the first one. And then it looks like the next note we came up with was 1. And anytime you mention a positive number, just mention it's negative. So we have 1, -1. Then we have 2, -2. And then, so we're here now, right? Then I have 1/2. So I'd mention 1/2, -1/2. Then I have 0, 0 again, and then I get 1/3. So I'd mention 1/3, -1/3. And then it looks like we end up with a 3. So then my next numbers would be a 3 and a -3. And then we would just keep doing that, right? So we're circling around that sort of that square there, right? And I'll leave it as an exercise to find the appropriate bijection that would describe this. Right, now what we've done here with our elements is we've really kind of have done that already, but we haven't given an explicit closed form formula for it. Right, because this is a one-to-one and onto relationship that I'm describing here, but I'm just sort of describing it in this sort of this list manner, right? I have all the natural numbers going to all of the rational numbers here. All right, so that concludes this video where we looked at different types of function properties. I hope you enjoyed, and I will see you next time.